look at the data dependence analysis and first define it, then look at one simple test called the GCD test, and then a more time-consuming test called the Fourier-Motzkin test, which was the basis for this was invented by Fourier in 1827 and then rediscovered several times, and it is sometimes called the Fourier test, such as in Bannerier's book, and sometimes called a Fourier-Motzkin test. Okay, so data dependence is, there are different kinds of data dependencies, and a true dependence is when one instruction or statement or iteration or something else writes to a value and then another reads that value. So we write that as S1 precedes S2, and S2 has a true dependence on S1. So we use the delta, and then which kind of dependence we saw earlier, that there was a control dependence, and that was marked as a C. It's always the one which should execute first, which is to the left side of the delta. Okay, well, there is not much to say, but there is clearly a data dependence between S1 and S2, since S2 reads what S1 wrote. Data dependencies can be at different levels. Instructions, for instance, machine instructions, or instructions in the intermediate code through address instructions. We sometimes call them statements, but in this slide, by statement we mean, well, statement in a high-level language. Typically assignment statements, but not necessarily. And loop iterations, between different loop iterations, between functions, between threads. And we will focus on dependencies at the loop level or instruction level. And parallelizing compilers, they typically look for dependencies between different loop iterations, so that some iterations can be executed in parallel. Instruction scheduling looks at both dependencies between instructions and loop iterations. Clearly, instruction scheduling needs to know about the dependencies between instructions, but also using something called software pipelining, we can execute some iterations concurrently. And these iterations, they are close to each other. So we saw true dependence. An anti-dependence is written like this, and instead of first writing and then reading, we do it in the other way. So first read and then write, overwrite what was read. And we should not, obviously, change the order of two such instructions. Output dependence is if we have two instructions which both write to the same memory location. And input dependence, that's if both read the same, which can be useful to detect that we have an opportunity to optimize cache behavior. We have temporal locality. Okay, well, there is not much to say about this. It's very trivial. And we move on with perfect loop nests. A perfect loop nest is one which has only assignment statements in the innermost loop. And also the loop bounds, lower and upper bounds, are linear functions of the outer loop index variables. And clearly for the outermost loop only with constants. And then here we can have, well, in this example, we can have P2 can be a constant and a multiple of I1, etc. So we are not allowed to have an if statement, for instance, and we are not allowed to have assignment statements except at the innermost. The reason for focusing on perfect loops is that they are frequent and they are much easier to optimize. Well, what we have is just a sequence of this statement. This here, there can be any number of statements, but we can view the innermost loop body as one piece, and we can change the iteration order so that we run, maybe switch these two loops, for instance, if that is advantageous. And that's much more simple to do, and if all the assignments are in the innermost loop. So here is an example of a perfect loop nest. When we say assignment, we only mean assignments to variables except the loop index variables. They are not counted here because they can be easily regenerated somehow. But we are not allowing assignments to the loop index variables in the innermost loop. We're not outside either, except when we increment the loop variable. So we have the following loop bounds. For the outermost loop, the loop variable should be at least, I mean, it starts with P10 or P10. And then the next loop variable, it starts with a constant plus a coefficient to I1. What we do is that we rewrite this as follows. So we say, we just rearrange this and have the constant alone and put this like this. And we can continue with the third loop variable. So we always keep the constant here. And that makes it easier to represent the loop bounds. What we do is to have this inequality, and this is a vector. I is a vector of loop variables, and P is a matrix. So this matrix is as follows. And we do the same thing for the upper loop bounds. And then we have this system of the loop bounds. And this is useful because if we determine that two iterations may refer to the same element of a matrix, and one of them is a right, then it's very important to know whether this iteration that we have found have referred to the same, if that iteration actually is in the loop, within the loop bounds, otherwise we can ignore it. Okay, so here we have an example of non-perfect loop nest with an assignment that is not at the innermost level. Okay, so what can we do about that? In some cases, such as this one, we can duplicate the loop and put this part in one loop and the other in another loop, like this. And then we have two perfect loop nests.